And now I'll talk about vector quantization, and the idea is very very important, right. So actually Gaussians and these are sort of related, as I keep telling you that I was talking about table of measurements, and basically we will come to that. So quantization, there are many applications. Okay, one of the important ones is that if you look at numbers, the way we represent numbers, right? We often have to represent numbers using computers, and computers have only finite precision, right? So you have memory locations that are of finite width. You can have 32-bit, 64-bit, whatever you want, right? But I cannot represent with infinite precision. What do I mean? I cannot have it like 5.33776544, for the millionth or billionth. It depends on the floating point and what all kind of representation that I use for numbers. But there's only a finite set of values that I can represent in a computer. Beyond it, of course, it'll hit the max, right, or whatever it is, and therefore, for example, if I had, typically you would have seen in high school and all, if I have only 4 bits, right, or 2 bits, for example, or even 1 bit. In 1 bit, I can only represent 0 or 1. Only 2 numbers I can represent, right? If I have 2 bits, I can represent maximum 4 different values. I can map it, right? So 0, 0, 0, 1, 1, 0, 1, 1, right? These are the 4 bits. I can map these 4 to some 4 values, right? That's all it means, right? If I have 8 bits, I have 2 to the power of 8, so 256 different values, right? That's all I can represent. I cannot represent infinite set of values, right? So that is the whole point of this quantization. So that is quantization in the sense of numbers, and that's true even when we transmit, right? We can only store finite with finite precision. In real world we can never have infinite precision, but most of our computers, they are very very the precision that they offer is pretty good, right? It's we can do a lot of useful things with whatever precision we have. Okay, so that is one case, right? You saw this kind of quantization even here, right? So we even if you look at the heights and the clusters that you saw here, right? So yeah, see, even here I am quantizing. Am I not quantizing? If you measure the height, if you have a precision, right, really good way of measuring height, right, or weights, right, I can say 50.6677888 kgs, right. I can go for a 10th decimal place, 15th decimal place, but normally even here, right, the table that I have, right, it is quantized because I see it 4 feet 11 inches, 5 feet 5 feet 1 inches. So I am taking in steps of 1 inch, right? So everybody who's close to 5 feet, so we will be doing some round off, right? If it was 5 feet, 0.00033 inches, right, then I will still make it as 5 feet, right? So even though my measurement might be very accurate, right, with a more number of decimal places, I will round off, right? For many applications, this is more than enough. I don't need to have that kind of precision that you're talking about, right? So the quantization happens in most real. We also round off, right? Even now, 50 paisa nobody gives, right? We always round off to the nearest rupee, right? So we are always quantizing, right, in life, right? We are not saying, hey, give me 3 paisa, 1.03, so give me 3 paisa. Now 3 paisa doesn't exist, na? So we always have to round off, and so many real world problems. Anyway, quantization is a natural phenomenon. Okay, so now the idea of Gaussians came. Now I am also going to look in a kind of the clustering or quantizing or vector quantization for data, right, without not like models, but some kind of a representative class and so on, right. So sometimes we often take this approach also for many problems. So it's good to know how we do. So one is a Gaussian kind of, or mixture of Gaussians kind of a fit that we apply, right. Another way is to just directly take the data itself and manipulate the data, and so you should know that this is also used quite often. So we will worry about this in the next class. So I'll start with that in the next class. Okay, yeah.